As the number of interconnected apps, users, and systems continues to climb every year, developers must try to keep up by pushing out the most dynamic web applications possible at an ever-increasing pace. But increased speed can come at a price, and the threat landscape of modern applications continues to grow, creating more vulnerabilities for hackers to find and exploit. Creating secure web applications starts at the developer layer, and knowing how attacks are executed will help you better understand how they can be remediated and prevented. My name is Cody Beers, and alongside Rachel Andrews and Chris McIntyre, we will be delivering a series of webinars that cover the top vulnerabilities affecting web applications today. So whether you're a software developer or an amateur InfoSec enthusiast, come along and join us for a crash course in web application security. Here's a little preview of the upcoming topics that we will be covering throughout this series. Up first is XSS, then SQL injection. We'll also cover API injections, directory traversal attacks, and finally remote code execution. Also, please be aware that this list is tentative and may change over time. To kick things off for our first webinar, we'll be discussing cross-site scripting. XSS is one of the most prevalent vulnerabilities on the web today and can also be one of the most dangerous and damaging attacks as well. In today's session, we will be exploring XSS in all its glory, including what it is, how it works, why it works, and how to fix it. Please remember, this is a crash course, so we won't be able to cover everything in full detail, but we will go well beyond the high points. And one more thing before we get started, it's important to point out that the information presented in this webinar is for educational purposes only. Don't do anything illegal, follow the laws of your local and state governments, always get permission before testing any sites you don't own, and finally, any software used during these webinars may be inherently vulnerable to web attacks. So be sure to follow all safety protocols outlined in the instructions of each piece of software. Okay, let's jump right in. What exactly is cross-site scripting? Here are two definitions of cross-site scripting from OWASP and WASC, but essentially XSS is when an attacker is able to inject or embed malicious scripts into an HTTP response from a web server. The script modifies the existing code being returned by the server, which can then be forwarded to an unsuspecting victim's web browser. JavaScript is at the core of XSS and is also fairly synonymous with the internet. The prevalence of XSS, as well as the dangers it brings to users and hosts alike, make it a primary attack in any web hacker's arsenal. There are a few key identifiers that can help a researcher detect XSS. The first marker is if user input is taken and directly reflected in the response object. This may or may not be intended functionalities on the web page, but the reflected result is still the primary indicator we have XSS. Next, we look to see if the HTTP response returns potentially tainted input with little or no security constraints. If the response reflects on the web page exactly as entered, or with minimal filtering, we consider the input to be improperly sanitized. If that unsanitized input can also be executable JavaScript code, you now have all three key markers for a cross-site scripting attack. It should be mentioned though that this is not a guarantee XSS is possible, just that this attack vector in question might be vulnerable to XSS. We can put this another way by saying that since the input is reflected to the user and not sanitized, the victim's browser can interpret malicious script as valid code to be executed. Putting it bluntly, a developer allowing unsanitized code into their web page is inherently leaving their web application vulnerable to attack. Okay, we now know what the key identifiers are for XSS, but what would someone actually do with a malicious block of code that they've created? How would they find their victims and deliver the payload? Well, since cross-site scripting attacks are typically via GET requests, the most common delivery method is malicious URLs being sent through emails into IM chats, hoping for a victim to click on the link. The attacks can also be persistent in nature, where the location of the vulnerability resides on the server itself and not in a crafted malicious URL. These kinds of attacks can cast a wide net, victimizing many users who are able to visit the corrupted portion of the website on top of those who are successfully phished. There are a lot of ways an attacker can leverage XSS. Credentials, cookies, session tokens, all can be stolen or overridden. Even denial of service attacks, malicious URL redirects, and remote browser control are all possible with XSS. Just to note here, about 38% of all applications tested at White Hat have at least one XSS vulnerability. And as I mentioned on the previous slide, the usual XSS payload is in the form of a malicious URL. To further expand, let's say the attacker takes an existing URL and modifies it in such a way as to inject their malicious code in an existing or new section of the folder path or query string. The first example injection here is on an existing value of the parameter named sort. The attacker changed the value of newest to instead contain a malicious injection. In our second example, we see an arbitrary parameter value pair being appended to the end of the unmodified URL. Either of the parameter, value, or both could be infected with malicious code. And in the last example, we see an existing folder path named widgets being changed to yet another malicious injection. Notice that all of these injections occur after the domain, and in case it wasn't obvious, if we injected on or before the domain, we wouldn't be submitting requests to the right web server. Although the URL is typically where XSS attacks are directed, there are other avenues as well that could be used. For instance, it is also possible to perform XSS by utilizing the parts of the HTTP request. One such attack point is the HTTP headers, and common targets are the user agent and the referrer headers. These two headers often show up as reflected HTML in the response object, making them prime candidates for XSS. Cookies are another possible attack point, and just like injecting on a URL, header and cookie injections can be done by modifying existing parameter value pairs, or they can be arbitrarily added. In the case of cookies though, it's important to check the value portion of the pair for specific encodings. A cookie's value may be encoded with hexadecimal, base64, or other encodings, meaning the injection might need to be encoded the same way, as it will be decoded at some point by the web server. Attacks on the URL are typically GET requests, but POST request objects can also be attacked. Common POST requests are made by completing registrations, logging in, updating profiles, as well as sending other PII via tokens and other custom functionalities. If you notice, these are fairly sensitive fields, and this is because the parameter value pairs and post bodies are automatically encrypted when sent over HTTPS, while GET request pairs are never encrypted in the URL. It's important to note that the post body and headers are encrypted when sent over HTTPS, but the URL of any request, including the query string, is always sent in the clear. XSS injections on headers, cookies, and post bodies are crafted exactly the same way as normal GET request injections. Now that we know what XSS is, we can take a deeper look into how it actually works. And let's make sure we have the proper tools in our arsenal before we get going. First thing you'll need is a somewhat modern web browser. This can be of your own choosing. However, we at Whitehat typically use Firefox due to it being less restrictive on testing for XSS and other injections. Once you have your browser picked out, you will also need a proxy tool to be able to intercept requests and test the responses with ease. Tools such as Zap or Burp Suite are perfect for this. Finally, put on that white brim fedora and tip it gently towards a testable web server. Moving on, there are three main types of XSS. Reflected XSS is when an attacker finds an injection and crafts a malicious URL. They will then send the unsafe link to an unsuspecting victim, where clicking the link may be all that is required to be exploited. And when I say unsafe, I mean that the link is embedded with the injection and will oftentimes be heavily encoded with special characters to avoid detection. Stored or persistent XSS is when the injection resides on the server, potentially victimizing users who don't even click on an attacker's link. These attacks oftentimes do not require a malicious URL to be crafted, merely an unsuspecting victim who either stumbles onto the infected page by accident or clicks on what appears to be a safe link from a phishing attack. Finally, there's DOM-based XSS, and DOM is the document object model of the rendered web page. And this attack is when the existing JavaScript on a page is manipulated in such a way that the exploit occurs entirely within the browser window of the victim's machine. DOM XSS is considered to be client-side, while reflected and stored can be either client-side or server-side. For today, we will only be looking at reflected and persistent XSS. DOM will be covered in the next webinar of the series. Alright, so let's break down reflected XSS a little bit further. Reflected cross-site scripting is probably the most common type of XSS injection. This attack is when malicious input is directly served back to the end user without being stored somewhere on the server's infrastructure. This attack is usually over a GET request, so the likely attack vector is in the URL's folder path or query string. The primary target for reflected XSS is anywhere that text is taken on the web page and directly output back to the user's browser. Username fields, search queries, and comment boxes all fall under this category and make primary targets for any vulnerability researcher. Error messages are often not properly monitored for malicious input, so these can be high-value vectors as well when testing for XSS. So now that we understand that a reflected XSS attack is when the injection is entered and served at the same time, it would make sense that a stored XSS attack is one that is persistent in nature. These injections exist permanently on the internal server's file system or database. This type of attack casts a wider net, as it can victimize unsuspecting users of the website who don't even get phished by the attack in some way. All they need to do is stumble across the injection by sheer chance. Stored XSS injections make for perfect phishing attacks, since the attacker can use safe URLs with no embedded injections for their phishing attacks. For all intents and purposes, the link appears to be 100% safe. Common targets for stored XSS include forum posts and message comments, since they allow an attacker to abuse an existing system where users interact with each other's content. Additionally, error logging files and updating of profile pages can create persistent XSS, but truly any locations where malicious code can be stored server-side and served to other users make for prime targets. There's one last thing before we start jumping into some injection examples, and that's landing spaces. But first, what even is a landing space? Well, it's a way to classify the type of injection required by looking at where specifically in the code does the injection reflect or persist. There are 4 different types of landing spaces. These are text space, attribute space, URI space, and script space. It's important to recognize what kind of landing space your injection is residing, as it will help to narrow down what types of injections and encodings will or won't work in that given space. To expand, let's take a look at text space first. This landing space exists anywhere that the injection is being rendered as plain text HTML. It will typically land between HTML tags such as header, paragraph, and body, and successful injections on this particular landing space usually require the creation of at least one new HTML tag on the document. The standard proof of concept injection is just script alert script. The script tag creates a new JavaScript code block, and the alert function is an unmistakable identifier of JavaScript being executed on a web page. The alert function isn't the only way to prove XSS on a website, but it is the go-to POC for most tests. Using this knowledge, let's try an example where we are able to inject on the plain text residing between an opening and closing paragraph tag. Instead of benign plain text, what if we take that basic POC injection and slap it between those 2 P tags? Well, the text on the page is now HTML tags with JavaScript code, so when the browser loads it up, it will execute the valid code, and we will see an alert box pop up on the screen.
Let's look at our first example of XSS in action. This web application is called BWAP, or Broken Web App, which is an inherently vulnerable web application like WebGoat or the DVWA. Testing XSS means that we want to get every parameter tested possible, including form fields and parameter value pairs in the URL. On this page, there are 2 text fields for input, one for first name and one for last name. Let's submit a test injection and see what the output looks like. I'll be using WHS and check to determine what kind of landing spaces we are hitting. Pressing go, we see that the output is reflected in the web browser with seemingly no alterations. At this point, we can right-click on the reflected text and use the View Page Source option to see the raw HTML of the web page. We can now use the browser's Find tool to look for our injections. As you can see, we are landing inside HTML text space, specifically inside of a div tag. Let's focus on the first name field, but we will need to leave the last name filled in as well, as the web page requires both for form submission. Since our landing space is HTML text space, we can try the simplest injection of script alert script, and inside the alert box, we will try to view the document.cookie object as our proof of concept. Press enter and we immediately see the injection fire, revealing the contents of all the cookies for our current session. Viewing the rendered source again, we can see the HTML syntax we injected is valid and not filtered or sanitized in any way. Awesome! We have successfully proven reflected XSS is possible on this web page. Now let's take a look at a persistent injection using good old WebGoat. This page has a simple tool that we can use to create and view form messages. We will focus on the message body, so let's add a benign title and the same injection before as WHS check. Submit the form, click on the newly generated HTML web link, and we can see that our WHS check injection is reflected as expected. Using the Inspect or Inspect Element option, we can view the page source as it is rendered in our web browser. Viewing the source this way, we can see that the injection is landing inside an HTML table, specifically a table data tag. Let's try another live injection, and this time we will place the script alert script in the middle of our WHS and check strings. Once again, our payload's target will be to display the document.cookie object of the user. So let's submit the post, click on the new link it created, and show our proof of concept for persistent XSS. The injection is stored in the database alongside all other forum posts, so the website can serve our malicious code at will, with no continued injections necessary. Anyone who clicks on our message or is directed to the URL where the message is located will be victimized by this attack.
Now let's move on to the second landing space, attributes. HTML attributes are the name-value pairs that exist within an HTML tag. The attribute information is always defined within the starting tag, and all HTML tags can have attributes. As an example, here's an input tag with two attributes. One is the type being set to text, and the other is an arbitrary parameter named param1 with a value of something. After testing, we find that the something value can be injected upon with whatever input we choose. But unlike the text space examples, we can't simply create a script tag with an alert function, as we need to ensure that our injection creates valid working code. So if we remove the old injection and add some spaces, we can see that where we are actually landing is between a set of double quotes. The first thing we need to do is break out of the attribute where we're landing so that we can gain more control over the code. In this example, breaking out simply means adding a new double quotation mark as a delimiting character to pair up with the first one after the equal sign. The param1 value is now closed, meaning the empty value will be executed in the browser. Now we can add executable JavaScript in the form of an HTML event attribute. These are attributes that can be triggered by specific actions or occurrences within the user's window. In this case, the alert function will execute anytime a victim clicks on the vulnerable input field generated on the web page. Notice that the existing close quote and greater than symbols are utilized to complete the input tag so that the code is error-free. The onClick attribute is just one of many HTML event attributes, which provides attackers a wide array of possible injections and attack methods to choose from. These 5 are but a small sample of the over 100 options to choose from.
Okay, let's try something a little bit harder. For this one, we have a shopping cart with a couple of input fields below for credit card payment information. Our target is going to be the input field for the PIN, so our first injection once again will be WHS check. Using a properly configured burp session, we can intercept the traffic from browser to server by hitting purchase on the web form and see the intercepted request now halted at the proxy layer. To be able to replay this request, we can use the repeater function in Burp Suite by right-clicking and select Send to Repeater. Click on the Repeater tab and we can see our intercepted request in the window below. Hit Go to submit the request and see the raw HTML response object in the right window of Burp. Using the search feature, we see that WHS check is reflected in 2 different locations, one at the top as an error message, and also in the input field where we entered our injection. We'll ignore the error message for now and instead only look at the input field's attribute space. Since we need to ensure there is valid code to be executed, the first thing we need to do is break out of the single quotes surrounding our injection. Notice that the injection lies in the post body of the request assigned to the parameter field 1. We will modify the request in Burp by adding a single quote delimiting character, then add a space, followed by an HTML event attribute to execute JavaScript. In this case, we will type on mouse over equals single quote, and then finally enter our alert statement. The original single quote and closing angle bracket will complete the injection syntax, and we can hit Go once again to test this. The syntax appears correct, so we can copy the injection from the post body and paste it into the input field for the PIN. Press purchase again and we can see that the WHS check injection is still showing up. This may either be because the program has filtered our injection in some way, or because our code is properly formatted and is being rendered as HTML and JavaScript accordingly. If the injection works as expected, we should see it fire whenever the victim moves the mouse cursor over the input field for the PIN. And there you go. We have yet another proof of concept for XSS, this time a reflected attack over post request landing inside attribute space.
Script space injections can occur anywhere on the page that executable scripted code already exists and can be injected upon. This code can be between script tags or even the contents of an HTML event attribute. The example here shows a segment of HTML code that contains a call to the eval function, which will write something onto the document. So let's assume that something is vulnerable to injection. One way to prove XSS in this context would be to break out of the JavaScript command and try to put our own code in there instead. To do this, we will first need to close the parentheses for the write function, then close the quotes around document.write, and finally close the parentheses for the eval command. Adding a semicolon successfully terminates the JavaScript line of code, and now we can add our own JavaScript code. We will use the alert function again, but notice that the trailing parenthesis and quotation mark characters will cause errors when rendered in the browser. In this case, we will need to terminate our alert call with a semicolon, and then add double slashes to comment out the last 4 characters. This is now valid JavaScript code and should have no problems executing when the browser loads the infected page.
For the next 2 examples, we will go back to BWAP and try to find some vulnerable JavaScript code. For this test, we do not have any text fields to manipulate on the web page. The only functionality is that the current date and time are displayed to the end user. Viewing the source of the page, we can see that the information displayed originates from script space, specifically a JavaScript eval call to execute the date function and write it to the document. Examining the URL, we see that the date function is being passed through the query string parameter of the same name. We can test this vector in several different ways. First, we can just modify the date function to instead be alert document.cookie. Submit this request, and as soon as the page loads, our injection fires, thus proving XSS is possible. Another injection we can try is by breaking out of the landing space, very similarly to how we did with the previous attribute space example. After intercepting the request and sending it to repeater, let's change the parameter's value to be WHS check and look closer at the specific syntax of where our injection lands. To break out of this space, we will first need to close the document.write function with a closing parentheses. And next we must break out of the eval quotes by adding one more double quotation mark, close the parentheses pair, and terminate the command with a semicolon. Now we can add our injection, so we put in alert document.cookie, terminate the command again with a semicolon, and finally let's add some double slashes to comment out the rest of the pre-existing code. After submitting the request in burp, we can see that our injection appears to be valid JavaScript code. Now we can test this injection in the browser by copying the full injection and pasting it into the date parameter in the URL. Press enter and the JavaScript code fires immediately. Cool! We found 2 ways of executing XSS on this web page. Let's try to find one more method we could use. Since JavaScript is a programming language, we can attempt injections that aren't possible in other landing spaces, namely math injections. This is when we use math operators to combine strings together, where at least one of those strings is our injection. We can use addition, subtraction, multiplication, and even the modulus operator to perform these attacks. But please be aware that the plus and percent signs are reserved characters for URLs, so these will need to be encoded for certain attacks. For this example, we will use multiplication. Similar to the last injection, we need to break out of the document.write function by adding our own closing parentheses and double quote characters. However, we don't want to completely break out of the eval function, we just want to perform a math operation on the divided set of strings. Now we can add an asterisk for multiplication, our currently infamous injection, alert document.cookie, and another asterisk to multiply the second string with the first. We'll add a double quote to match the trailing quote after the closing parentheses character, submit the request, and the response object returns properly formatted JavaScript code, including our malicious injection. Let's make sure it fires by copy-pasting again, and there you have it. Script space is probably the trickiest landing space to execute injections, so be sure to pay special attention when dealing with these kinds of tests.
The last landing space we will go over today is URI space. This space is a subset of attribute space. Specifically, anywhere an attribute's value is set to a URI that is able to be clicked or loaded in some way. Some examples of this space are hypertext reference attributes found in an anchor or area tag, and source attributes used for iframe, image, and audio tags. Since this space is a subset of attribute space, an injection here overlaps with a standard attribute space injection. So all that needs to be done is break out of the href attribute, create a new name value pair, and XSS can easily be proven. But what if double quotes and parentheses are being filtered out on this attack vector? So you can't even break out of the href attribute, let alone execute the alert statement. Well, we can actually make use of the href attribute to execute JavaScript code when the rendered hyperlink is opened by a victim. To do this, we will need to use what is known as the JavaScript URI scheme. The formatting for this scheme is simply to type JavaScript : and then the applicable code to be executed afterwards. Notice that since our injection is being filtered in some way, it instead uses the URL encoded values for open and close parentheses, which are %28 and %29 respectively. When the victim clicks on the link, their web browser will decode the URL encoded values correctly as parentheses, and the injection will fire as expected. Now let's try a little more complicated URI space example by trying to inject on a data attribute of an HTML object tag. For this vector, we will be using the data URI scheme instead of the JavaScript URI scheme. We can use data : instead of JavaScript : and the text, HTML, base64 all indicate to the browser what kind of data to expect. By passing a base64 encoded string with the prerequisite identifiers, we can inject seemingly benign code into an object that's expecting a URL. The browser will decode this string when the object is loaded on the page, and the malicious code will be immediately executed.
For the final demo, we'll be looking at a test page that I created specifically for this webinar. In this example, we see there is a URL in the query string, and it is reflected on the web page inside of an anchor tag's href attribute. Since URI space is a subset of attribute space, we could try to break out of the attribute space by adding a double quote and use various techniques we've learned today. Instead, let's try to use a URI-specific injection for this potential vulnerability. Within URI space, we can use the JavaScript URI scheme to try and inject some of our own code. So let's first try to remove the current URL in the query string, and instead we will input JavaScript : alert document.cookie. Submit the request, and we can check our injection by clicking on the link, and instead of the document's location changing, it will execute the JavaScript embedded within the href attribute according to the URI scheme. Our injection works, and we have proven XSS is possible on this web page. We have now covered the basics for all 4 landing spaces, so let's switch gears and see what kind of actions can help us prevent XSS going forward.
Finally, let's briefly look at filtering and remediation techniques for XSS. A web application firewall, or WAF, is a server-side layer of protection between end users and the server's infrastructure. A WAF protects web apps by monitoring, filtering, and blocking any potentially malicious HTTP requests defined by a set of rules or policies. A WAF can help protect against cross-site scripting, SQL injection, CSRF, and many more attack types. WAFs make use of regular expressions, or regex, to either allow or deny specific content access to the web server. Additionally, all modern languages have syntax matching using regex, such as pregmatch for PHP and regex.matches for C#. If the regular expression dictates specifically what is not allowed, then that is considered to be a block list item. Block lists are harder to manage as new attacks and new injections become possible over the lifespan of an application, and it is nearly impossible to catch everything. Block listing will more than likely slow down an attacker, but it probably won't stop them entirely. If instead the regex pattern specifies what is allowed, then we would consider that to be an allow list item. Allow lists are easier to manage than block lists, as there is usually a defined set of characters or strings that are expected for a given functionality. This means that instead of hunting down all possible attack vectors and ensuring a block list policy exists for each one, we can instead use an allow list to define which characters, IP ranges, and strings are specifically allowed, thus preventing most of the unwanted requests from making it past the WAF. To further demonstrate why allow listing is the preferred option, let's pretend we are managing a WAF and we notice potential XSS injections using the alert function. Well, with a block list, all we need is simple regex pattern to prevent the alert function from triggering. We escape the parentheses with backslashes and voila! The alert function is now completely banned. Wait a minute, now the attackers are using the prompt function instead for their attacks. What are we going to do? Well, all we need to do is add a new regex pattern. And presto! Alert and prompt are now both successfully banned, and we can even clean up this regex to make it a little bit neater and nicer to read. But hang on a second, now the attackers are using the confirm function to test XSS. And on, and on, and on. This method is entirely exhausting, and you will end up chasing your own shadow trying to stay ahead of the attackers. So instead, let's try an allow list and see what we think. For this example, let's assume that the input field should only ever need to accept alphanumeric characters as well as the hyphen character. So here's what our regex would allow. And that's it. We don't need to concern ourselves with every single attack vector imaginable, just the ones that fall within the scope of the allowed characters, which is going to be close to 0 with this particular char set. And in case that didn't clarify allow list's advantages over block lists, feel free to start writing some regex that will capture this injection. So the preferred and most reliable means of thwarting XSS attacks is to encode any and all untrusted data. These sources include user input, database queries, and files served by the network. It's also important to remember to encode all data output to the end user as a second layer of protection. Be mindful of the location the data is being output, as different encodings work differently in the various landing spaces. For instance, the double quote is a common character used in XSS attacks, but it can be translated into many other iterations that are readable to the web browser without breaking out of any pre-programmed syntax. Finally, input data should be carefully filtered against an allow list. This approach has the advantage that it can be performed externally without modifying application source code, and data retrieved from third parties or shared with other applications can be filtered alongside any user-supplied input. And that pretty much wraps up today's webinar, so let's do a quick review and preview. To recap, XSS is an attack where malicious code is executed by a victim's web browser. These attacks can either be crafted URLs, or they can be persistent on the server's database or internal file system. Using XSS, malicious actors can perform an array of attacks including stealing cookies and performing DOS attacks. The three types of XSS are reflected, stored, and DOM-based. When testing for cross-site scripting, injections can exist in various types of code, so it's important to be mindful of what the content and context of the landing space is. And finally, use input sanitization to clean up all user-supplied input, and use output encoding to prevent any potentially tainted data sources from executing malicious code. Our next webinar will focus on evading filters that prevent XSS attacks from firing. We will also dive into DOM-based XSS to round out this segment of the crash course. Thank you for joining me today on our first of many crash course webinars. As I mentioned, the next webinar will finish up the XSS portion of the course, and after that we will continue on with the other attack types. Once again, my name is Cody Beers, and I hope this webinar has been helpful for anyone wanting to learn the basics of XSS.